Good afternoon. Today we are going to talk about dynamic programming. We will talk about dynamic programming today. We will talk about it next week. We will talk about it in 14 days. And then we will occasionally return back to it again and again because dynamic programming is an important strategy in the whole in many areas of computer science. So as we will see, it is more or less not just one particular method. It is a strategy for tackling very different problems. I will present today few examples where we will get some taste of what's going on, and next time we will continue with some very specific famous examples. So what can we say at the beginning? So first of all, there are some important properties. The desired solution is composed of suitably chosen optimal solution. What does that mean? That means that typically we will have a recursive problem which we will divide into smaller sub-problems, and then we will solve those smaller sub-problems. And the method of solving smaller sub-problems is absolutely the same. We again divide those sub-problems into even smaller problems, and again apply division and division step by step, solving smaller and smaller problems, and then constructing the solution of the final big problem or of the original problem out of those smaller solution. And the method on each level of solution is the same. So it is, let's say, typical recursive approach. But what is important in dynamic programming, that typically it happens that those sub-problems, those smaller sub-problems on lower levels are typically not just similar, but completely identical. So you go into deeper and deeper level, and on that side you find a smaller sub-problem. On the other side there is another smaller sub-problem, and they are identical. So in the whole big recursive scheme, you do not repeat the solution of many identical sub-problems. You solve one sub-problem only once, and then you reuse those solutions. So that's an important feature of that. So you remember the solution of smaller subproblems in some table, as we will see in a moment. So that's the general it's not an overview, it's just a general quick view of it. The dynamic programming problems, or rather the problems which can be solved by dynamic programming, are, as you can see, quite various. You can talk about some parts in the graph, some problem with packing your backpack, some optimal scheduling of I don't know of what, longest common subsequence of some probably sequences, matrix multiplication, binary search trees, and so on and so on. Why and so on? Because there you can see, or rather you cannot see because the font is too small. This is a copy from Wikipedia, a list of typical dynamic programming problems, or of dynamic programming algorithms which solve particular problems, and the list goes on and on. So anybody interested in can go and check himself or herself. So let us see some nice example which should help us. The first example is here, and it goes like follows. Maybe I can make it a little bit more bigger. So what's going on? We have just a usual function. There is some function with two variables, as it is shown there at the top of the screen, and we have to compute the values in some particular points. Namely, here they suggest point 10 and 10, so it is two-dimensional. You can imagine it is in two-dimensional plane, x and y, and you have to compute f or compute z, for example, value of the function. So what you do, the prescription is there at the top. So what you do is you say, all right, I have the prescription, so I can easily produce a code which is there in the middle of the picture. And with that code, what do? Well, you just run that code, call the function, and get the result. So what is the fuss about? As you can see, or maybe you cannot see it yet, there are some repetitive calculations hidden in this process. Of course, they are repetitive because the function, as you can clearly see, is a recursive function. So what you do is, well, you call it recursively, and nothing extra happens. But you might ask easily yourself, well, if it is recursive, you can easily assess the depth of recursion. In each step of recursion, as you can see in the middle of the screen, in each step, one of the parameters is decreased by 1. And when we call the function, we call it with two parameters, 10 plus 10. 10 plus 10 totals 20. And therefore, when in each step of recursion, we decrease one of those parameters by 1, so surely after at most 20 calls, the one of parameters will be 0. Probably, maybe surely after 19 calls, one of parameters will be 0, and the recursion will stop. So there will be at most 19 levels of recursion. Let's say 20. Let's say 20. So there is the recursive solution f 10 and 10 goes into depth. Let's say 20. With depth, let's say 20, you say, well, the 20, that's not too much. But on the other hand, you are quite aware that we are in fact in recursion, and that recursion is represented by a binary tree of recursion. Tree of recursion. And the tree of recursion, how does it look? You call f with parameter 10 and 10, and to get that value, as the middle of the screen tells you, you have to compute f of even 2 times, but that does not matter. F of 10 and 9, and also f of 9 and 10. And to compute those values recursively, you of course have to compute other values, which I am not going to draw them all here, because we will see it on the next slides very probably. But what is important, that the depth is 20, so the depth 20 is here. This is your binary tree, so if this goes into the depth 20, and there is some action on each level, in fact there are more and more actions on the next level, so there might be about 2 to the power of 20 nodes in this tree, and therefore 2 to the power of 20 calls of function calls in this tree. and 2 to the 20 is about 1 million. So the size of the tree is in order we don't know exactly, but that's not important. Is in order of 2 to the 20 nodes. Nodes that, of course, corresponds to function calls. And okay, so we have 2 to the 20, which is about 10 to the 6 or 1 million. Now you say, aha, good. So what's going on? First of all, you notice that if anybody will ask you to compute, for example, f of 100 and 100, which seems simple and easy, then you will, of course, immediately see that this tree, the whole, which describes the whole computation, will be quite a deeper one, namely 10 times deeper, and the number of nodes will be not 10 to the 20, but 10 to the 2 to 200. And well, is that a big number? I don't know. It is surely what it is 2 to the 20 times 10, isn't it? And that 2 to the 20 is 10 to the 6, so it is 10 to the 60th power. Well, which is bigger than the number of atoms or molecules in observable universe or something like that. So we can see that even with a very small functions, classically, the problem is trivially too difficult to compute, and still we have to do something very simple. The function, which you can see, is not difficult to compute, and what you can do, therefore, you say, okay, just to verify exactly this stuff, you just include one global counter in the function call. And there you say, well, what we do with this counter, that counter is increased each time we make one recursive call to the function, and finally, when we compute the function value, we just print the counter, and it is not 1 million, it is 1/3 of a million. So, but still the order is more or less the same. So 1/3 of a million to compute such a small number. So let us. Well, why does that happen? Of course, I have. Started the picture here. There is a better picture on the screen where you can see what's going on. We have to compute the function value for various possible combinations of input parameters. Those are both of them should be 10 or smaller. So there are in fact only 100 or maybe 121 possible input combinations, provided that the parameters should be non-negative, 11 times 11. But there are millions of different function calls. Therefore, many of them, as the picture shows, must be the calls with the same input parameter. Therefore, they must be with the same output parameter. So what you do, of course, you say, no, I am not going to compute the value of this function by recursion. What I am going to do is that I am going to store all the values of function calls with the different input parameters, and there are not too many possible combinations of input parameters. So what we do is we just jump to to the next part, and here it is repeated, and say, okay, let us create a table. Here on the left and on the top there are values of input parameters up there, and on the left side there are y parameters from top to bottom, and into the table we store the function values. But of course, how do we compute those smaller function values with smaller parameters? We of course do not use recursion. We just refer to the prescription which is at the top of the picture, and which says, okay, if you want to compute something which is there in the middle, in one particular slot of the table, then what you have to do, you have to refer to the value of the function with the second parameter smaller by 1 multiplied by 2. You can see there is this round arrow which says take f of x and y minus 1 and add to it from here from left, add to it function value of x minus 1 and the same y parameter. So that means that we can completely, when calculating the values, completely forget about the recursion itself. Well, maybe not completely, but to some degree, yeah. And of course, the function prescription, which is there at the top, changes into the scheme which is in the center of the slide. So how does it look in practice? In practice, it looks like this again, in the middle or in slightly below the center of the slide. There again is the repeated scheme. How it is computed? Well, I can 0, 1, 2, 3, 4. Those are x values. Y values would be 0, 1, 2, 3, 4, and so on. I'm not going to copy it whole here, just to show you how simple it is. Whenever any of the parameters is 1, then the function value is, whenever any of the input parameter is 0, the function value is 1. So you fill this with 1s. As far as you can, you fill the first column or 0th column with 1s as far as you can, and then what do you have to do? You have to take the upper one, multiply by 2, and add what's on the left when you want to fill in particular slot. So you take 2 times 1 plus 1 is how it is 3. 2 times 1 plus 3 is 5. 2 times 1 plus 5 is, let's do 7. 2 times 7, 9, probably 11. The method is obvious. 1, 13, 15 would be there next, 17, and so on. On the next line, the process is repeated absolutely without any change. 2 times 3 plus 1 is 7. 2 times 5 plus 7 is 17. 2 times 7 is 14 plus 17 is 31. 2 times 9, 9 is, now we are not, we don't have it on the slide, so be careful. 2 times 9 is 18, plus 31 is 49. 2 times 11, 22, plus 49 would be 69, but it isn't, it is 71, and so on. So what you do is that you have there to calculate f of 10 and 10, you create this table of size 11 times 11, and there in the upper, in the lower right corner of the table is the value of 10 of f of 10 and 10, and that it is. So the complexity which we saw in standard recursion simply vanished, and we just had this one table. Those of you who are into effective implementations might notice that when we compute the result, we even do not need to store the whole table in the memory, because it is always enough to store just 2 current lines. When we are creating the next line, we are always referring only to the previous line and not to the line above. For example, if we are going to fill in the line number 3, then we say 2 times 7 plus 1. Wow, it's 15, 2 times 17, 34, plus 15 is 49 again, but that's a coincidence, and so forth. So we refer only to the previous row. So our memory complexity is just 2 rows, and it is not 10 times 10 or n times m. It is just 2 times the smaller of the two parameters, if the parameters are different. So the memory complexity is small because you can use only two rows and to forget the previous ones. So this is an important idea of dynamic programming. Do not repeat the same things, which in recursion might easily arise, and put the results into the table and reuse the values which you computed previously to compute the next values. So the code is not much longer or shorter than the previous one. As you can see, just create a table and then to apply 2 loops, and those 2 loops just fill in the table. Maybe you can do, surely there is nowadays some extra Python statement which does it on 1 less lines. Maybe they can put together 2 loops or anything like that, and there it is. So of course, well, if you want to compute now a value of f with different parameters, so if those parameters are bigger, then you have to extend your table, maybe, or whether you have to compute the whole table. Again, that depends on you and on the circumstances. What I wanted to present here is the main idea. So having this, we can go and see some other examples, which I hope will be even much more amusing. Before we jump into those, we have to make some 101 on graphs, or respectively, we have to recall some important details about graphs. So what is a graph? There are 2 examples of graphs at the bottom of the slide. On the left, there is a directed graph. On the right, there is an undirected graph. The difference between the 2 is that in the directed graph on the left, each edge has a direction. It's also called arc, or an arrow is on that arc or on that edge. It is directed always. You never mix it. There are some theoreticians who work with graphs which are half directed, half undirected, but typically in practice we don't want to do it, and we keep those two kinds of beasts separated. So there is a directed graph and undirected graph. Both of them can be weighted or unweighted, and again, in many situations, the weight is the cost of the or the value of the edge. So the graph describes some system of connections. So if you move through the graph from one node to the neighboring node, you traverse an edge, and the cost of the edge tells you either how much you pay, or in some cases it is how much you earn, or that depends on your particular situation. But very important is that the value is associated with the edge, and typically it does not change during the computation. So those are graphs with their weights, and many typical questions ask you how to get from one point to another point, along the edges, and of course either collect as much value as you can on the edges, or to pay, because that's the payment, the numbers might describe the payment, or to pay as low price as possible. Find the cheapest way. So those are typical questions, and some of them are difficult, and some of them are easy, strangely. So we have to distinguish between the two. So there is a short recall from other subjects, maybe what's going on. Optimal paths in graphs. If you are looking for a shortest path, you want to get from A to B in the cheapest way possible. It is a problem which is solvable, which is relatively easily solvable. We have a shipload of various methods which do that. Typically, you either apply breadth first search in most simple cases, and then there is Dijkstra algorithm, Floyd-Warshall, Bell-Manford algorithm, Johnson algorithm, and many more for more complex cases. And those typically find you the shortest path from A either to B or even to any other nodes, and they do it typically in time that, as they say here at the bottom, is quadratic in number of nodes. Floyd-Warshall run is in O(n) to the third power, but that is an exception because it does find you the distances between any two pairs of nodes. So that's not a problem. If you have to solve any of those problems, you just take a particular library and just run appropriate method from the library, and it does the job. Now, if you are looking for longest path, if you are going from A to B and you want to earn as much as possible, never return to the same state, because typically it is forbidden, either because it happens in time and you cannot return back to previous state where you were in, if the graph describes the sequence of states which might happen in some system, or simply you cannot return to a node because typically you use those resources there, and returning there makes no sense. So if you want to, under such circumstances, travel in the graph and find the longest path, then we don't know. It's an NP-hard problem, and as everybody knows, we don't know whether NP-hard problems and let's say NP-complete problems are solvable in polynomial time. So we don't have fast algorithms for solution. We have approximation algorithms and probabilistic algorithms, but we don't have exact algorithm for solution. So what do we do? Well, we can say, well, number one here, they suggest at the bottom, use brute force. Well, if you use brute force, it's an exponential. So when you have 20 nodes, or 20 of anything, 20, 30 of anything that we are computing, you are helplessly stuck. So that does not help. Then there are some approximate and probabilistic solutions, but those are a little bit advanced. So if you meet some of those in some next years in your master study, then all right, but typically not earlier. So we do not talk about them in this basic course. And what else can happen? Well, then you say, okay, we don't know how to solve it in general, but maybe in some particular graphs, in some particular situations, some simple, for example, if you've got a tree, so what is the longest path in the tree between two nodes? There is your tree. You want to get from A to B, and you are not allowed to return back to any node where you were previously. Then, of course, the longest path from A to B is this one, because it is the only one. There are no other paths between A and B, and in any tree in general, between two nodes, there is always one path. So in this very extra special case, the question how to find the longest path between A and B is absolutely trivial. There is only one path. It is the shortest and the longest at once. So it raises some hopes that maybe if the graph is a little bit more complex than just a tree, then maybe the complexity of the general problem again will not be that much. Maybe there will be some relatively simple algorithm which will reveal it in a graph which is for somehow tree-like. For example, if you admit only one loop in the graph, one circle, then, well, probably the complexity is not that much bigger. Now there are between any two nodes, there are at most two paths, so we'll compute both of them and choose the longer one, and that's the solution. So some graphs are relatively favorable, and if they happen in practice, then it's good. And one of those extra cases is a directed acyclic graph, as we will see in a moment. And we talk about the directed acyclic graph because typically we can process it by methods of dynamic programming, finding the longest path or finding the shortest path or finding a path with some more properties is typically done in the same way by a dynamic programming approach. That's convenient. So if you are given a dynamic acyclic graph plus some question about it, you typically say, well, very probably if we apply dynamic programming, that is solvable. And there are many directed acyclic graphs in practice, so it's useful. Okay, so let's jump into directed acyclic graphs. Before we do that, we have to see some example and simply understand what's going on in there. What is a topological order and why we will need it? Let's take a picture and let's see what's going on. At the top, there is a directed acyclic graph. First of all, it is a graph. That's obvious that it is directed. That's also obvious. And it is acyclic. It is not that much obvious. What does mean acyclic? There is no loop inside the graph. So it never happens that you start in some node, wander along the edges, and suddenly you return back to a node where you were previously. So this is a loop, or of course cycle. Yeah, fine. Or a cycle, and that should not happen. And that does not happen in the above graph. And how do we verify it? In the small picture, it should be more or less obvious, and in the bigger picture, we will see in a moment how to do it. So, at the bottom of the slide, there is the same graph as at the top, only it is shown in different topological topological setting. In fact, it is so-called topological ordering of the graph. It means that you have a sequence of nodes, not necessarily 1, 2, 3, 4, exactly according to the labels, but just in some order. And what is important, then all the edges go from the lower order to the higher order only and always. So, for example, let's have an example of a graph which is acyclic. When you start somewhere, you never can get back. Let's give them some names to the nodes, and now you want to produce a topological order. Sometimes there are more possibilities, as we will see. So what you do, say, well, if you want to start anywhere, you have to start in A, because you cannot get to A from anywhere else. So you start in A, and then you will typically go to C, then you will go to B, and then you will go to D. That's no, you will not go there, because you go to, excuse me, you go to D. I apologize for being absent-minded, and from D you go to B. So that is your topological order. This is this order, and what's left? We have from A to B is one edge, and from C to B there is another edge. So there is topological ordering of the graph which is below, and as you can see, the edges go from left to the right in one direction, in one spatial direction only, let us say. So this is the topological order of the graph. There are some more examples just to get used to the concept. At the top again there is a directed graph with the nodes labeled in some order, and first at the bottom part, at the bottom we have first the topmost row, then there is the middle row, and there is the bottom row of the graph, and the connections at the top are the same as at the bottom. The same graph might be also ordered topologically in a different way. At the top now there is the same graph as before. The nodes are labeled differently. Now they are ordered. Now they are labeled in by columns. So first goes first column, then the next column, and finally the rightmost column. And now you can store at the bottom. You can see that you can put the columns one after the other, and again set the edges so that the two pictures are the same. They are isomorphic, and this is another possibility. And there is also another possibility. Surprise, surprise! You can take number 1, 2, 3. And so on, labeled diagonally. So you first put the leftmost, topmost, topmost corner, and then you put 2 and 3 at the bottom. There you put next diagonal 4, 5, 6, 4, 5, 6 at the bottom, followed by the next diagonal 7, 8, 9, and so forth. So one topological graph sometimes might be sorted topologically in various ways. That does not matter. Typically, any topological order is, for our purposes, is as good as any other. So how do we discover that topological order in real life? And then there is some algorithm which tells us how to do that. Therefore, we can easily go and perform that algorithm. What the algorithm says, Well, in general, there is some initialization in step 0 and 1. We have just to put something into some queue. We put there the nodes. Nodes which in degree is 0 are in the queue, and then we just process the queue. We remove something from the queue, look at the neighbors of that node which we just pulled out from the queue, and optionally insert something else into the queue. Let's see how that works. So it is just your standard queue processing. Nothing strange is going on there. So at the beginning, there is on the top left is our original example graph with 9 nodes. And what we do first, there at the top on the left, upper left pictures shows the initial state. Into the queue we have put nodes number 1, 2, and 3. We just label them, just assign them those labels. 1, 2, and 3. They are in the queue in this order from left to the right. An important feature is that 1, 2, and 3 are the only nodes in the graph which have in degree 0. Therefore, it means there is no edge pointing into those nodes. For all others which are left blank on the in the left top left picture, there is always some edge going into that node. So now what we do? So we have this in the queue. So what you typically do, you say, okay, now take the first node out from the queue. That is the leftmost node in the queue. That is number 1. So you take it from the queue and look at all edges which go out from 1 and remove them from the graph. That means you don't have to remove them physically, you just mark them as deleted, let us say. And also, when you do that, you also decrease by 1 the in degree of the node which is at the end of that edge. So there, the topmost node on the right, in the right top, to which the 3 is pointing, and 1 as well. So that node had in degree 4 originally. And this one here at the top, there was 4, and now it is only 3. And we do the same for each edge going out from 1, and the result is, of course, what is left black on the right in the upper part. And not just that, if a node, after removing those edges which are getting gray, after removing those edges, if the node at the end of that edge suddenly becomes a new root, that is, there is no edge incoming, because into the 4 on the top right, there was the only edge coming from 1 was edge from 1 to 4. So now 4 is a new node without anything coming in. Therefore, 4 is a new candidate which is stored in the queue. As you can see at the top right, at the end of queue, there is 4 sitting in there. So we did this with node number 1, and now we do repeat the process again and again until the queue is empty. So we have to finish the first run of the loop, which we continue to do until the queue will be empty. So 1 is removed, and who is next in the queue? Next in the queue is number 2. So therefore we say, aha, we remove it from the queue. As you can see on the left bottom, it is not there. And when we remove it there at the bottom. And of course there is the only one edge going out, and the node into which it is pointing, there are still many edges pointing down it. So removing 3 didn't change too much in the whole graph. So it was removed from the queue, and and nothing was added into the queue. The same happens in the next step with node number 3. No effect of removing node number 3, and only node number 4 was left in the queue. That's the node in the middle, and when we remove it, we get to the next slide. Now 4 was removed, and suddenly the new node are 5 and 6, the nodes into which no edge is going. So 5 and 6 go into the queue, and the whole process continues as before until, and that happens always with the directed acyclic graph, that until the queue is not, well, empty. It is not still on this slide, but as you have seen, we step by step remove all the edges, and after a while, the whole queue becomes empty, and the topological order is given by the labels which we assign to each node in the process of removing them from the queue. So the first remove, second remove, third remove, and so on. Here is our topological order. So at the bottom there is the same graph as we had at the beginning. This happens always when the graph is directed and acyclic, when there is no cycle in the graph. If, on the other hand, the graph contains a cycle, then simply the topological order cannot obviously exist. So after a while, what does happen, that the queue becomes empty, and there are still some edges, the edges which are in the loops, which still remain in the graph, and that's how you find if a graph is acyclic or whether it contains some loops. So we can jump back to the description of the algorithm, and that description should be now clear. First, we took nodes number 1, 2, 3 and stored them in the queue. That's this part. And then we repeated the step number 2 while queue was not empty. We took a node from the queue, and for each edge going out from that node, we just removed the edge, removed that particular edge. And after removing that edge, we looked into the end node of that edge. And if after removing that edge, that in degree is 0, then that node which is at the end of the edge, we insert it into the queue. So in fact, when we are just checking or creating this topological order, we don't even have very probably removed the edge. Because we visit each edge exactly once, and what we need to do is to decrease the in degree. So the whole remove edge process might be just decreasing by 1 the in degree of the node at the end of the edge. So that is just one elementary arithmetic operation. So nothing else. So remove edge, it sounds important, but it isn't to do something much less complex. The complexity is on the right part of the slide. It's more or less, again, it should be obvious. We check each edge exactly once, and that's what we do. Therefore, the complexity is linear in number of edges and, of course, nodes as well when they are added together. So the complexity is standard 1. It cannot be too much faster. We check each edge exactly once. So it is a fast method, and that's it. That's it. We've got a topological sort. And now, so what? Fine. Where is the dynamic programming? I promised you dynamic programming, and where is it? Dynamic programming is just one step away. Let's go to it. find the longest path in the directed acyclic graph. I started with a statement that finding the longest path is difficult in general graphs. We don't know the exact algorithm. We have no clue whether it does exist at all. But in directed acyclic graphs, the problem is simple enough, and we can just scan the whole directed acyclic graph once and get the answer. So what do we do? There is, at the bottom, there is a picture which does suggest that we already have the graph in the form which is given by its topological ordering. We go from left to right, just in one direction, and we move just steadily in one direction. An important property is that we are always somewhere. Some part has already been processed, the results which are there are already computed and they are final. The nodes which are still ahead of us, they were not yet visited, they are not yet processed, and we will come to them later and we will compute their respective values in a while. Another important feature is that as we moved, we leave behind us everything done, computed, final, and therefore when we arrive to the very end and step outside the graph, at the end of the graph, there is complete information what we want to find, and in this case, it's the longest path. So how do we do it? There is some talk on the slide about the general approach, and maybe I can comment on that. So what we do? Let's imagine that we know the longest path in the graph which ends in particular node. So each node, when you take one node in the gray already processed part, in that part behind us, you take any node and you ask that it is processed, it knows everything. You ask it, well, what is the length of the longest path which ends in U? So that node says, it is written here, it is this part, it is there, exactly that one, I know it. So, so that is the information which is stored in each node. Each node knows what is the length of the longest path, it can even reconstruct the longest path which ends in there. Not the longest path which goes through that node somewhere else, not interested in that. It must end in that node. The longest path which ends here in this node. So that is the information we have in each node in the gray area, in the processed area. So as we move forward, we come to the new node, which is unprocessed, and we want to calculate this information. What is the longest path which ends in this particular, in this new node? What is the longest path which ends here? Using the information from the gray area where it is pre-computed, but for those nodes, it ends somewhere else than in our current node. What we therefore do is say, well, but when we are in the current node, which is yellow there in the middle of the graph, there are some edges going from the gray area to our node. So we look along those edges to the predecessor of our current yellow node, go to the orange predecessor, one of them is marked Y1, and we ask, and we can do it, we ask that Y1 what is the longest path which ends in U? Y1 gives you the answer, it knows it, and you say, aha. So if in Y1 ends this longest path, we can extend that longest path which ends in Y, extended by our edge going from Y to our current yellow node, and extended by the length which is given on the edge from Y to X, which is here at the top, and that's some value W1. So the longest path which ended in Y1 might be extended by the length of W1, and that's one possibility. What might be the longest path which ends here in yellow X? That's a candidate. We don't know, because absolutely the same situation happens with the nodes Y2 and Y3. They are also in the gray area, and there are some, very probably, there are surely some other paths which end in Y2. There is some longest path which ends in Y2. So we can again take now Y2, extend the longest path which ends in Y2 by the length of the edge from Y2 to the yellow X. And with those, now we have another candidate which went through Y2 into X. Originally, we had the first candidate which goes through Y1 into X. So now we have two candidates, and we compare them and take the better one. That means we take the longest of those two. Of course, we could compute them because we knew the longest path which ends at Y1 at W1, get the length. Take the longest path which ends in Y2, add W2, get another length, compare the two, take the better one. The same, of course, holds for Y3. You again take Y3, what's the longest path which ends in Y3, add the cost of going from Y3 to X, get something longer, and compare it with the previous candidate we computed for X using Y2 and Y1. So simply take the maximum of all those extensions. In this case, there are 3, but you can easily imagine there are 5, 17, 24, 200 of them. And that means that when we check all the edges which go from the gray area into X, then we can compute the longest path which ends in X, and therefore this information is stored in X, and we can move from the X to the next node in the topological order, which is just to the right of X. So this is the whole idea, and again, as you can see, when we were in X, we just looked back along one edge, along more edges, but along each edge we looked back only once. And from the previous node, we took information in constant time about the longest path, then extended the path, again in constant time, extended the length of the candidate path in constant time. And having that, all the actions which are associated with looking back along one particular edge happen in constant time. So therefore, the whole process, when we start at the beginning and then we step-by-step process each node, each time looking back along all the edges going back from that node, that whole process, again, will be linear in number of edges. So again, it will be, and it is fast process. So let us see the example. The next picture, which I am skipping now, refers to a little bit different approach, which is in fact the same approach, but that might be confusing at the beginning, so we skip it now. So the example, let's have a look at the example. There is the graph which is directed, which is acyclic, and is already presented in topological ordering to spare us the troubles of finding the topological order. We already know that it's an easy task which can be easily performed. So there is the graph, and now we have to find the longest path in this graph. So we start at the beginning on the left and proceed to the right step by step. So what we do, When we start in the leftmost node, that's the node labeled 0. And let's put it into the gray area because there is no incoming edge into the first node. Therefore, the whole information which is related to this node is that there is nothing coming in. Therefore, the length of anything which ends in node number 1 is 0. We also in each node will register a predecessor. That means the edge by which you arrive the longest path into that node. Not the edge, the previous node from which the longest path arrived. We will see it in a moment. So that's already there. So it is an initialization part. Of course, the predecessor of the first node is nothing. And now this slide shows us processing of node number 2, which is yellow, and there is one edge incoming into 2. So we look back along that edge and say, well, what is the longest path ending in our predecessor? The predecessor is number 1, and there is the distance is 0. So we say, aha, therefore we increase that 0 by 6, and we have length of longest path ending in 2 equal to 6. Because there is nothing else ending in 2, it is also the result for 2. So if you want to get into 2 in this graph and to travel along the longest path, you will travel exactly from 1 to 2 and collect or pay 6 units. So it is registered here at the bottom. The distance is maximum of just one number, which is 6, and predecessor, that P at the bottom, is number 1. So now we move, as you can see, to the next slide, which, as you can see, 1 and 2 already were processed. And because 1 and 2 are already processed, this means that we are talking about node number 3. And we look back along now, those are 2 edges. And we take the first one, the top one, which weight is -2, and it goes from 1. In node 1, the longest path has length 0, plus -2, that would be length of -2 in total. On the other hand, the bottom edge from 2 to 3, which weight is 2, that adds to the longest path, which ends in 2. And we already know that in 2, the length of the longest path, which ends in 2, is 6, as I have just highlighted here. So we take this 6 and add to it this 2, and that is this 6 plus 2. So that's another candidate of what is ending in number 2. And those are those 2 possibilities. It is either 0 plus -1 or 6 plus +2. Maximum of those is 2, is 8, and it is attained on, of course, the edge from 2 to 3. Therefore, the predecessor is the predecessor in 3 is set to be node number 2. So let's continue. Next slide will be absolutely the same as these 2 previous. We just now move into node number 4, as you can see. And being in node number 4, what happened? That again there are 3 edges ending in 4. So again you do absolutely the same process. Check all possibilities, either getting from either getting from number 1 there at the bottom, that corresponds to 0 plus 8, either getting from 2 directly going to 4 along the edge, which costs us 3, that is 6 plus 3, because in node 2 the value of longest path is 6. Either you take this 8, which is in node 3, and add -2, which are along the path from 3 to 4. So we collect these 3 values, do the arithmetic, and out pops number 9, which is attained, of course, at 6 plus 3. So the longest path, which ends in 4, where it is the predecessor is 2, and in 2 the predecessor is 1. So you can easily reconstruct the path. It is this go from 1 to 2, and then go from 2 to 4 along the edge, which weight is 3. So there are other slides in the presentation, but those slides will hopefully tell you nothing new, because they just step by step repeat the whole process which I'm just presenting. So I will go through them very quickly now, because there's nothing extra. There are 2 edges ending in 5, so we consider 2 possible predecessors. In both cases, they are both decreased by -1, not today, but the values of the longest path ending in the nodes, and that is 7, and therefore the predecessor is number 3, because in 4, because in 2, of course, it is much smaller. In 3, the value is bigger. So we get to the predecessor is 3. Move to the but last node. What happens in there? There are 4 edges ending in 6. So you process them in the same way. And when we are ready with number 6, just to conclude, we arrive to node 7, which is the last in the row, the last node in the graph, in the topological ordering, and we process it exactly the same as all previous nodes. In fact, when we process the node, we even do not know whether some nodes to the left, to the right, still do exist or not. So the last one is processed in the same way as all the previous ones. We get those values calculated as before, and now is the time just to put everything together. In each node, we have the weight of the length of the longest path which ends there, and also we have the predecessor listed in those nodes. So now you take the first row of the values we just calculated, this one, and find the maximum there. That's number 14, and then just move along the predecessors back from 14. You have to go to 6. From 6 you go to 4. From 4 you go to 2. From 2 you go to 1, and there you stop. So that is your shortest path. So as you can see, the only important part of the whole process was that the graph was directed and acyclic. There are never any edges, confusing edges going back to the left, and the problem of finding the longest path is effectively solved in linear time in number of edges, in time proportional to the number of edges. I just have to, before that, I just recapitulate the algorithm we have just seen. First, we have to register distance and predecessors. They tell us, well, good. Now we go through all nodes, And we say that the distance is the distance of the longest path, which that's there initialize it as negative infinity, and they have no predecessor. So this can be done easily. Now we have to take the nodes in ascending the topological order. That has to be done in the previous phase we saw before. And then we just do what we do for each node. Therefore, with each node, what we have just done, what we do, we take the edge which ends in that x from y to x. We are in x currently for each node x. Excuse me. And for each node which goes from some previous y to our x, what do? We just check trivially what is the best. Whether the current distance of x is smaller than the distance which goes first to y and then moves along this particular edge from y to x. Yes or no? If yes, if the distance going from if the distance of the length of the longest path going through y into x is bigger than what is currently registered in x, then we do register in x that particular new distance, and of course register a predecessor to be y. And that's all we have to do. At the end, at the end, what we say when we have processed all the edges which come to x, y1, y2, minus 3, minus 2. Let us say that there are some distances in y, or let's say there is nothing. What is the longest path which ends in x now? When we are in x, if we are in y, if this is the whole graph, the longest path which ends in y1 is obviously has length 0. The longest path which ends in y2 also has 0 length. And when we are process x, we would be tempted by the algorithm to say that the distance of x is maximum of those two, which is minus 2. But that would be nonsense, because you can do better than that. You can simply neglect and say, no, our path will have length 0. So we will not consider those edges. Our distance in x is in fact 0. But if everything is negative, then of course don't opt for the negativity. Just stay at 0. So you do need this small piece of algorithm, and that's it. The complexities are again on the right, as you can see. There's nothing too much to worry about. What then is there? There might be some small difference in the whole process. Sometimes when you think about these kind of problems without even knowing about dynamic programming and directed acyclic graphs whatsoever, you might yourself discover this method. And typically what might happen that you might discover it from a different point of view. And that is the point of view which is on the right part of the slide. On the left part of the slide, there is what we already know. The code is repeated, at least the part 2, because the initialization is the same all the time. And this approach, I repeat, looks like we always look back what happened before, and according to that we set the value for the current node. The other take on it, but with the same, absolutely the same result, is such that we in fact process when we are in a particular node. We take the last, we consider that node to be the last in the gray area. So each time we take the last of the nodes which are already processed completely, and we take the edges which point forward. And we say, what do we say? We say, aha. So we are now, here we know, because we are in the gray area, here we know what is the length of the longest path which ends here. So we can now, looking into the future, move along the edge which goes outside. There it is from X going to orange Y's on the slide, and say, okay, so if we arrived to X, longest path, then we can extend it and give it to node Y as a candidate to their own longest path which ends there. Of course, later sometimes it might happen that Y will communicate. Later it might happen that other node than the current one X, for example, the blue one, which is here between X and Y, might have some edge which goes also to the Y node, and that node will tell the orange Y node at the end a different candidate longest path. So that means that the whole process goes like this alternative point of view. First, we say if our distance in our node in which we currently are, and which is the last node we know everything about. So if the distance is negative, we set it to 0. That's not typical, that does not happen that often. But what is important that we take each edge which is going for each node X, that is going from X out forward, and what we say, we look into Y and say, well, if the current distance of Y is smaller than distance to our current node plus the weight of the edge, then we do and update the distance in Y. So we do updating in node Y distance from the standpoint of our current node X, and we do it only once. But there are other edges going into Y from the right, so either before, either later, we will also consider some edges from some nodes which go also to that same Y, and each time we will upgrade, or maybe upgrade, the information in Y. So when we finally, in this processing nodes, finally arrive to Y, we will know that in Y there are already all possibilities how to arrive optimally to Y are checked. So therefore in Y everything is computed, and again we apply the same strategy looking from Y forward. So those are these two approaches. They are completely equivalent. As you can see, the implementations are absolutely nearly the same. So it does not matter which one you use in your implementations. So that's this part. Just typically, some people tend to tell you in dynamic programming, you always look back to previous solutions, to smaller solutions. From those, you construct a bigger solution, and then you move forward and again construct even a bigger solution. Again, looking back using those smaller solutions, where that's the approach which is on the left. But you can, if somebody comes in and says, well, I do it my way, it's absolutely all right, no problem. So let's just see one warning. The warning which refers to the non-negative edge weights. So this part which checks if the distance if the distance is negative, and if it is negative, it rewrites it back to 0, and length 0 of the whole path should be applied in case when we have also some negative weights on edges. Typically, some programmers tend to live only in non-negative numbers, and if they leave it out, leave the condition here at the bottom, if they leave it out, they might arrive to improper results. So in this respect, be careful when you Google out the solution. There are many zillions of solutions, of course, everywhere, because it's easy to program and to present, and be careful that you might just copy and paste the incorrect program, which it forgets about the possibility of negative edges. Otherwise, everything is fine. So what is on the last slide? On the last slide, we have something a little bit outlandish, but not that much, because it asks us, well, we have found some shortest path, and okay, but what if somebody comes and says we want to all longest or shortest paths? For example, you can have something like this, and you can say, well, we can go here by 6, and then by 2, which gives us 8, and maybe we can go here by 1, and then by 7, and there is another path which weight is the same, and I don't know, I put this 2 there, so not to get confused, this way, or maybe still you can go here in the middle, you can put the 5, and again you can get from the beginning to the end. Oh. Yeah, the more I try to wipe it out, the more it is dirty. So this was number 2. So there are many possibilities how to get from the leftmost node to the rightmost node, and with the same maximum length. 6 plus 2 is 8, 1, 5, 2 is 8, 1 and 7 is 8 as well. So they might ask you, well, what about reconstructing all optimal paths? Why would not you go for that option? One path. We want to know many different paths. If they are all optimal, then they are all optimal. But then when we know all of them, we might choose according to some additional criteria which one we want to use. So this last slide warns us just be careful in such cases, because, well, they present us with a simple graph, which is here on the left, and what they say is it has a simple structure, and all the horizontal edges are the cost of each horizontal label is the same. It is A, which you might imagine is 26.42, and the vertical edges are also labeled. The cost of vertical edges is also the same. You might imagine anything else you want, 43.26. And in that case, let's have a small example, like 4 times 4. Any path which goes only right and only left, there are only these possibilities. These possibilities of movement. So any path will move 1, 2, 3 steps to the right and 1, 2, 3 steps to the bottom. Each cost of each horizontal and of each vertical step, they are the same. So therefore, any path you choose to move in that graph, for example, like this, the cost of the paths will be always the same. And now, okay, all are optimal. And how many such paths are there? And as you can see, they give us here the answer. If the n is 40 times 40, then the number of paths is the number which is there at the very bottom of the slide, which is very simple. Which is very long. How did they find it? They find it using method of dynamic programming, of course. Just to have a look on it once more. Take a graph like that, and how many shortest paths and in a particular node. So if we start here at the top in point A, in node A, then to get anywhere in the topmost row, there is only one possibility how to get there, because otherwise, if you don't follow this path, you have to go down, but then you cannot get back to the topmost row. The same holds, of course, for the first column, and then you say, and how many ways? In how many ways can you get, for example, here to A prime? Well, it is the sum of the two numbers. You can get to the left of A prime in one way, and you can get to the top of AY by one way. So you total those and you get to 2. And you continue the same way here at the top. If you get here in 2 ways, and here in 1 way, therefore you can take 2 ways and each of them extend, or get there to the top, and then there is only one possibility, of course, how to extend that to one possibility. Therefore you end with 2 plus 1, which is 3. And the same idea applies and to all nodes all the time. So here we have 1 plus 2, here we have 3 plus 1. There are 4 possibilities how to get to this node. Now it goes up quickly. There is 3, here is 3, so here is number 6. 6 and plus 4 is 10. 6 plus 4 is 10, and here already we have 20 possibilities how to get there. So again, we are using, in fact, the dynamic programming idea. In how many ways you can get from A to B, not the length, but just the number of those ways. And it is the number of ways we can get to all direct predecessors put together. There is 10 possibilities, there is 10 possibilities. So you've got 20 possibilities. What will be on the next diagonal element? I've got no clue. The 3, 1, 2, 3, 5. 5 plus 10 is 15. 20 plus 4 is 35. Therefore, here will be 35 as well, because the situation is symmetric along the diagonal. And you will have 35. 35 is 70. So as you can see, the number grows quite quickly, and that is confirmed by the list we have on the slide. So that is why we don't go, at least into this course, we don't go into the question give us all possible shortest path, because in realistic problems that might be quite impossible technically to do. Theoretically, it is perfectly possible. You just recursively go through all possibilities and reconstruct those paths, but of course that might not fit into your machine. So that would be all for today. Thank you very much, and the next time we will go and see more examples of dynamic programming. Have a nice day.